Good afternoon. Last time we finished this point on operations on processes in Unix-like systems that influence the memory image of a process. There are two such basic operations, fork and exec. Families of processes are created just using those two calls. Exec not necessarily, because we can just code the behavior of a process family in single program. However, if we consider, for example, shell that runs programs on user demand, a pair of operations of fork and exec are used to operate on user programs. Let us start with fork. Fork creates a clone of a process. The code of the clone is one-to-one, so physically the code is not copied, the code is shared. Data area is almost one-to-one, but almost means that a copy of program data must be made. The differences between a process that is the parent and the child are twofold. First is the result. Result is 0 for child and non-zero for parent. Non-zero is process ID of a child process. The other differences are in system data area. For example, process ID. It is different for a parent, different for a child. And similar differences can occur in system data. In user data, only this single cell of memory, the result of calling fork. So if we assume the memory image of a process to contain code and data, and we have a function with local variable and static local variable and parameter that is referenced inside the function, and dynamic object that is created in the function. So we can find all those variables in data area of the program, but specifically the parameter is passed on the stack. The local variable of a function is on the stack as well. Static variable is in static data area, regardless if it is between functions or in function. If it's static, it is declared in static data area. And dynamically created objects like malloc, new function, you know those functions, especially new object, they are allocated on heap. Heap is just large area inside data area in which all dynamic variables other than local variables in functions are allocated. Okay. And this code, the code of this function is of course in compiled version, the version compiled to the machine code of the computer is somewhere here in the code. What the fork operation does. Having those two areas, code data, compound with system data, with process ID being P, the code area remains the same. It is shared for the parent and child, but a system must know how many processes use the same code area. So there is a usage count in the system that remembers number of processes that use this code. After fork, it is incremented. For the parent, data and system data remain the same. For child, a copy is created in which data area is almost the same as parent. The difference is the result of fork. And system data is almost the same. Some subtle differences can occur. And different process ID is for the clone, different from the parent. So if we assume that the result of fork is on the stack, typically it is on the stack, the complete data area of the program consists of data area, system data sticky to this data area, the code, and set of registers. Don't forget that the program operates on registers and stores some values, intermediate results in registers. So we must take into account the registers. For example, datum points to the beginning of this data block. Limit is the end of this data block. General purpose registers store some values. It is defined by the compiler what values are in registers. We can have register variables, for example, in C. Stack pointer points to the top of the stack, and program counter points to the current position in the code. So if we are executing fork, program counter points the body of the library fork function that contains syscall fork. When we clone the process, the code remains the same. So program counter in both parent and child appoints the body of the fork library function. Stack pointer appoints the same position on the stack, but it is different stack. Why? Because datum for the child is different. Those two registers, not accessible to the user programmer, are filled by the operating system. So datum of the parent appoints data area as before, but for the child, a new data area. The same for leave it. And the result of fork is on the stack, and the value is different for the parent and different for the child. Let us think about the mechanism which is used to copy the registers. We see that parent and child have separate sets of registers. How it is done? Recall what we said about context switch. When we execute a syscall, what happens to registers? Recall this information. What happens with user registers if we perform arbitrary system call? What happens? Could you tell me? They are pushed on user stack. So during execution of fork in the kernel, the registers are on the stack. When we copy this stack area, we copy registers as well. We copy registers accessible to the user. Some of them are in process descriptor, namely datum and limit. And what register accessible to user program cannot be pushed on the stack? This term. There are address registers for calculations, stack pointer, frame pointer, program counter. You know those registers. Which of those cannot be pushed on the stack? It can be pushed on the stack, but without any sense. Physically, yes. But it has no sense to push this register on the stack. Which one? What? No, frame pointer can be pushed. Stack pointer. Stack pointer defines where is the top of the stack. Push registers, other registers, they are pushed relatively to the content of stack pointer. We cannot retrieve anything from the stack not knowing the stack pointer. So stack pointer should be stored separately. The only register that should be stored, typically, of course, in process descriptor. Okay, but most registers are on the stack. When we copy this data area, we copy registers as well. we only should modify datum limit and stack pointer. Because they are out of the stack. The second operation is exec, execute a program. The parameter of exec is the file that contains the program. What happens if usage count for the code of the parent process is n? Oh, we cannot say that this is a parent process, because before and after it is the same process. No new process is created. So the usage count of the process is n. After exec, data area is replaced by data loaded from the file prepared by the compiler. Compiler prepares some data area where some elements are filled and others are just reserved. What is filled by the compiler? Texts, hello world, or other texts. Static variables with initial value. Parameters of the program. For example, needs for some areas that are read by operating system, and the operating system acts accordingly. So they are, well, some data are filled with information, most are only reserved. But system data remains the same, with subtle differences. But generally, it remains the same. So please tell me, thanks to not erasing system data, what the program called from the disk takes from calling program. What data? What data are given to the called program for free? System variables. Data area contains system variables. I showed you the set operation, yes or not, last time. I don't believe, but we can look at that once more. Of course, it is not Linux, it is Windows, but the mechanism is similar. I didn't show it to you? Yeah. So the child process gets not the copy of those system variables. It gets those variables, not a copy. If we create a new variable, it will be available to the called program. The same what is very important, the same applies to open files. In system data, we have a table of open files. So if we have an open file by the program, this file is open in the code program here. If we start reading from the file, for example, we read 100 bytes, and the code program will read from the file, it will start reading from the byte number 100, not number 0. Because in open file table, we have the pointer of current position of reading in the file. Yes, you understand this mechanism? Okay. And what happens to the code? It simply is decreased. Oh, here is on the border. It is the usage count is decreased by 1. Because this program no longer uses this code, it uses new code loaded from the file. Generally, it is costly. Why? I will stop this presentation. And I will show you where it is. Oh, I don't have this. I have it only in Polish. Nevertheless, I will translate. Most is in pictures. Okay. How shell works? No, it is fork. It is not this presentation. Shell. Oh. How the shell works? Of course, it uses fork. How the shell works? The shell works in a loop. It reads a line from input stream. It can be a keyboard or a file, a script file, and executes this line and reads the next one and so on in a loop, in a circle. After reading, it executes. How it executes the program? First, it reads a line and parses it to the program name and parameters. Program name is name of the file that contains a program. Parameters are parameters. They are strings, simply. So it parses S to program name P and the rest R. In this example, the rest is empty, so we have only a program name. We have a program name. What the shell does? It forks and parent waits for finishing the program, giving as parameter the process ID of the child, and the child executes the program. Why? Why a new process is created for that? To return to the shell after executing this program. It is the simplest case. Let's look at somehow more complicated example. We have execute a program A assigning file X as input. You know this syntax, yes? It is used in Windows as well. So, after reading the line, shell parses it to the program name, and the rest is not empty. The rest is X. Of course, it must cut the less than character, but it is a detail. So, shell forks as before. Parent waits for finishing the child as before. But the child closes standard input, opens file in variable R, it is X. With handle 0, it is standard input, and then executes the program. So the program has its input redirected to file X when it starts, because the child has system data area of the parent, and the parent of the calling program. And the calling program is the child in fork. And it has the same file open of the child shell opens the file, and called program has the same file open, because system data does not change. Oh, it is similar example with redirection of output. It differs only in the number of handle. Stream 1 is output, but generally it is the same. How we can run the program asynchronously? What means asynchronously? The called program runs, but shell displays the prompt without waiting for finishing this program. The solution is simple. Just the parent does not wait for the child. We just reject waiting. No more. Now, execute two programs, sending output of the first to the input of the second. So in one line, we execute two programs. What the shell does? It forks two times. After first fork, the parent waits for finishing the child as usual, but the child, it creates a pipe. Why this program creates a pipe? Because the pipe will be used between those two programs called from shell. So the first level child of shell creates a pipe and forks. And we have second level child, the orange one. The first level child closes standard output and redirects standard output to writing to pipe and calls first program A. The second level child closes standard input, redirects reading to the pipe, and calls the second program B. That's all. Okay. The rules are obvious and simple. However, there is one disadvantage of this scheme. Let us take just simple call. The shell has a parser, error detecting and recovery, the interpreter of for loop, while loop, conditional execution if. So it is quite large program. The rules are simple, but there are many other activities that performed by shell. So the shell is not such a simple program. But see, we copy data area of the child or of the parent, and from those data we use only very small part, namely the result of fork, not more. So and we override those data with data of the program code program. So we do much work without a purpose. We copy large data area, then we reject this data area. We use only small element of this data area connected with fork. The rest, the data of the parser, of loop organization, conditional statement, large parts of code are for variable handling in scripts. It is a large program with large data, and we use only very small part of this. And we copy those large data, then we reject all of them because we load the data of the code program. In some systems, non-standard operation of fork exec combined. It is non-standard because it is not described in POSIX specification. More compact and faster for those systems if we have such combined fork exec system call. But it's out of standard. This problem is solved other way, which I suspend this discussion. We'll return to this when we learn some rules of paging. Because most systems nowadays are paged, and special paging mechanism is used just to hide non-efficiency. Okay. We return to our were specific to POSIX systems. Now we discuss more general rules of memory allocation. How we divide memory for allocating this memory to programs. Three rules are used. First is no memory division. Entire memory is allocated to program that is run. This rule was in DOS systems from Microsoft. If a program wanted to run another program, it must create some memory area inside itself to run next program, because the entire memory is given to every program that is run. When we run a program, the entire memory is allocated to this program. So there is no memory for other program. And it must create some area inside itself to run another program. It was extremely complicated. But this mechanism is used in IoT, for example. When we run a program, and a program on exit specifies next program that should be run after this program. So in some single application IoT devices, this rule is used. The second is static memory partitioning. So we just cut memory into pieces statically. And we run programs in those partitions. Why? Because we do not deal with cutting blocks, joining blocks, searching for blocks, moving blocks. It is just simple and efficient. Again, in IoT, static memory partitioning is a good solution. And dynamic partitioning is cutting dynamically blocks of memory and allocating them to given programs. Oh, this we can skip because it is with no allocation. Oh, when we allocate the entire memory for the program, typically the program will not use the entire memory. Parts of this memory will remain not used. It is called fragmentation. fragmentation as a phenomenon is no possibility or limited possibility to use memory that is not used. Internal fragmentation is fragmentation inside allocated blocks. We allocate a block larger than the program demands. So part of this memory will not be used. It happens in, for example, in static allocation. Or when we quantize the allocation. For example, we allocate the multiple of 4 kilobytes. And the program uses 3 kilobytes. So 1 kilobyte is lost. It is internal fragmentation. Of course, most modern systems use partitioning, but specific partitioning if it's page system. But now we discuss systems without paging. So it is simply partitioning. It can be static or dynamic. Of course, it supports multi-programming. And external fragmentation is creation of small, not allocated blocks that are too small to use them effectively. It's external fragmentation. Let us look at static allocation to fixed blocks of various sizes. We have two versions of this rule with individual input queues of programs or with common input queue. Let's look how fragmentation arises. First, let's look at internal fragmentation. For example, we have operating system, then we have blocks of 100 kilobytes, here 200, here it's 300 and 100. And programs with given size are allocated to those input queues. If we run a program of 2.5 kilobytes, the rest of this partition is not allocated. It is external, internal. It is internal fragmentation because we allocate the entire block. External fragmentation can happen as well. When we allocate a program of 100 kilobytes into this large partition, of course, internal fragmentation occurs as before, but external fragmentation can happen as well. In this solution, when we have free partition 2, free partition 3, a program from queue of partition 2 cannot be run in partition 3 because it is in another queue. So we cannot use this memory this part of memory. It is external fragmentation. It is out of allocated blocks. Suppose that the programs in Q have those sizes showed as the size of the program is proportional to the length of the bar. Partition 2 is free. What I must recall, what is this case? Okay. Oh, here we assume that the programs are run in the order they are in the queue. This program cannot be run because it is too large to fit the partition 2. Dynamic partitioning is based on several system calls, internal system calls. Of course, they are not called by the program. It is allocate a block of given size, which returns the address of this block. Very often use change size. We do not imagine how often programs call this syscall. It is the best example is a compiler. The compiler, while compiling a program, creates a symbol table of the program. Names of all entities in the program, functions, variables, labels, whatever. It creates the symbol table. Typically, the initial size of heap for the compiler is not so big. So it is enough for compiling small programs, but not enough if we compile large programs. For example, when we compile a compiler, this technique is called bootstrap compiling. When the compiler, we prepare a new version of compiler and we compile this with the old version of compiler. So it has enormous number of variables. When the symbol table cannot allocate new variables on heap, the compiler calls operating system to enlarge data area of this compiler. That's why in modern solutions, heap is the last data area in the program, because if the data area rises, the heap rises because it is last in order of sub areas of the program. And compiler can call this change size several times, because several times it can happen that there is no room for new identifiers in symbol table. It can be costly because it can happen, and I imagine that it happens very often, that after the program in memory, there is another area. So we cannot enlarge. We can enlarge only by moving this program to other place in memory. So it can be complicated. Release is just freeing the memory, and inform is checking if there is enough memory block to run the program. It is from Tannenbaum, as you see, on the violet background. External fragmentation happens in dynamic allocation. We allocate programs A, B, C, A finished, so we have two holes in the memory. We allocate D, and we want to run A again. We have enough memory, maybe this memory together with this, but they are no adjacent. So it is external fragmentation. Here, after finishing of B, there is enough memory and we can run A. It's external fragmentation. Only when we run program in stack-like fashion, external fragmentation does not happen. We run A, then B and C, C finishes, B finishes, A finishes. Surprisingly, such situation often happens due to manner of calling program in Unix-like systems because of this mechanism of call and exec. Because the calling program remains in memory. It forks before calling the target program. In the context of multi-programming, we use datum and limit registers. Datum is used both for relocation and for protection because we cannot access memory below program 0. Limit is used only for protection. It does not play any role in relocation. Limit is only for protection. This was about division. Now let us look at allocation. The rules for allocation. There are generally 3 algorithms for allocation 3 blocks: first fit, best fit, and worst fit. Next fit is a variant of first fit. You see here it should be listed. It is in Polish. We are in first fit. The list of blocks is unsorted. We just or at the end of the list, wherever. When we allocate a block, we just search through the list to find a block that is enough for a given program. It is equal or greater to the demand. So here we have the required size of the block and the list, and we check the first too small, second too small, third too small, fourth, okay. We extract this from the list, we allocate it, and the rest that is over the demand, we add to the list. It can be quite small, you see. So in next fit, we start from the position that we finished last time in searching. If we finished with this block, we start here. The next is okay, so we take it, we cut the rest and add to the list. Best fit is to create the possible smallest rest blocks. We look for the block that fits the needs of the program best in the list. So the list is sorted increasingly. And every new free block must be sorted into the list in correct position. So we compare with the first, not enough. Second, not enough. Third is large enough. We take it, we cut the rest, and we put this into the in order to the list. The weak point of this algorithm is creating large list of small blocks, which are just for nothing because they are too small to run any program in the beginning of the list. So it is the reason of inventing where sorted from larger to smaller, and we always take the largest one first from the list. It's enough, so we take it, we cut the rest, and insert into the list. And some special algorithms for allocating memory. Buddy's algorithm. It's dynamic allocation. However, we do not take blocks of arbitrary lengths. We always cut free block if it is too large in some constant ratio. Typically 1:1 on 1:2. This is an example. Demand is this size, memory is much larger, so it's too big. We cut it by half and check again. Now, this block is again too big. So we cut it to halves. This one is correct because it is larger than demand multiplied by 2. And we allocate the block, and the rest becomes fragmentation because we do not allocate this memory to anyone. This algorithm creates a problem when we divide memory, and from the history of allocation, we have accidentally 2 blocks occupied on lower and upper memory, and 2 free blocks in the middle. they cannot be mixed. They cannot be merged because they were created not in leaf division, in the tree of divisions. We must wait for example, for this to disappear and we can merge this one with this one or this one with this one when they are two blocks of upper and lower memory, finally we can merge them to the common large block. In this situation, we cannot merge those three blocks because they come from different divisions. And one more algorithm used in Unix-like systems, we realized that in Unix systems, it's typical that the programs are run in stack-like order. That means the parent waits for the child to die. But the child can run another program, so the child can incarnate to other code and other data. And this algorithm takes this into account. For example, we run a program that has code and data on separate edges of memory. The middle is always free in this algorithm. It is called onion algorithm because we can imagine that this is an onion slice, and this part and this part are from the same shell in the slice. When we fork, data is duplicated, but code remains the same. Another does not work. Another fork, and again, data is duplicated and code remains the same. Exit, it is program finish, deallocates this data area. And exit deallocates this area. Exec changes code and data to another code and another data. But they are at the same places as, of course, the size of them can differ, but they are on the two tops of two stacks. It is another fork and exec. Exec allocates new code and changes the data. When the parent exits, we see that two holes are created. In this situation, the system shifts them up and down. So always the middle is free memory block and single free memory block. I cannot judge if it's a good idea or not because I did not analyze it in operation, but I believe that it can be quite effective because of the nature of calling programs in Linux. These are the criteria to select given algorithm for memory allocation. The speed and simplicity, of course, they are connected, and the effect of fragmentation. I have a question to you. Knowing what is the internal of external fragmentation. It can happen in memory, but on another data capacitors like cache or disk, they can happen as well. So let us judge. We have a program typically in operating systems. In Windows, it is when we click the right hand button on the disk icon, so we can defragment the disk. The program is called defragmenter. So my question is, what kind of fragmentation does it remove? Internal or external? Both? What do you think? It's a tricky question because this program does not remove any fragmentation. It is called defragmenter because it changes fragmented allocation to continuous allocation of programs. But external fragmentation, or let us start from internal. Internal fragmentation occurs on disk when we allocate some data block to the file, but we do not use the entire block, but we cannot remove this fragmentation. If it's allocated, it belongs to the file. External fragmentation is out of the blocks. But if we have not continuous allocation of files, we can allocate new part of the file in arbitrary part of memory. So external fragmentation does not exist on this. So we cannot remove it if it does not exist. So defragmenter just changes fragmented allocation to continuous allocation. It does not remove any fragmentation from the disk. Oh, it's tricky. Okay. Not to create small rest blocks in allocation, we can define some quantum of memory that is allocated. So, for example, if the quantum is 4 kilobytes, we cannot create free block of 3 or 1 kilobyte or half kilobyte, because we always allocate multiple of 4 kilobytes. So it is acting against external fragmentation, but it enlarges internal fragmentation because the program can get more than it demanded. Merging blocks. If two blocks that are adjacent become empty, we can merge them. And of course, we must make the correction to the list of 3 blocks. It is contracting fragmentation. And costly but used is compaction. This is example of compaction. We have memory that is entirely allocated. And one of the programs in segment 1 finished, and in this area we allocate a new program that is smaller than previous one. It should be program, not segment. Oh, it can be segment if we have segmented memory. Okay. So we have 3 kilo of free memory. Here, program 4 finished we start program 5. Again, it is smaller, so we have 3 kilobytes empty. And this program finished, we allocate a new program 6, 4 kilobytes are free memory. So totally, we have 10 kilobytes of free memory, but it's external fragmentation, and we cannot run a program that occupies 5 kilobytes or 7 or 10. But we can move those programs to the edge, upper or lower, not important, and create large free block in which we can run program up to 10 kilobytes. This is compaction. Why it is costly? First, in large memory, this process can last for minutes. Second, while the program is being shifted in memory, it cannot run. Part of its memory is in old position, part in new. This program cannot run, and typically the program stops, the operating system stops all the programs for the time of compaction. How the memory is mapped in the operating system. Generally, there are two manners. First, that can be used only in quantized memory. Every quant of memory has a bit in memory map. It is obvious that it should be quantized, because if not, we should have a memory map for every byte, which is not reasonable. Every byte requires single bit. So it is only for quantized memory. And we have a map of allocated and free quanta. The other is in of blocks allocated. Program starts from 0, 5 blocks. Whole starts from 5 free blocks. Program starts from 8, 6 blocks, and so on. And this is the end of the list. Some null pointer. Typically both are used, because we need to learn about the memory allocation from the perspective of memory, it is memory map, and from the perspective of programs, it is the list. So typically both are used in parallel. Segmentation. Of course, we talked about segmentation many times because it was required discussing some mechanisms. For example, when we discussed Linux programs, they have code area, it is code segment, data area, data segment, and system data. Engineers realized that different parts of memory are used in another way. We differently used code and data. Some parts of memory should be executable, some non-executable. Some should be read-write, some should be read-only. If we have a table of constants, it is best to keep it in read-only memory. When the program code and data were in the same data area, of course separated, but with no barrier between them, we could jump to data or execute data or treat instructions as data. Data as instructions. Of course, viruses love to read the program code and modify it. So they decided to separate physically those areas. Such a way, the idea of segments arise. Memory of the program is cut into parts called segments. Every segment is addressed separately from virtual zero. So it has its own datum. And different access rules are useful for those segments. It was quite effective. However, it complicated the addressing in the program, because the program should point to which segment the instruction refers, because all segments started at 0. For every segment, we have a segment descriptor that is loaded to the processor when the program runs and has some important information about the segment. This is an example map of segments of a program. In days when segments were used extensively, binary code, data, constant, stack, source code for the debugger, for example, symbol table, shell data. Segmentation allowed to build a version of virtual memory. So it was a milestone in development of computers to run more programs that fit into primary memory of the computer. How? Simply some segments or entire sets of segments of programs can be swept out to the disk. So those programs totally can be larger than primary memory. In beginning of Linux, of Windows, of Unix, this mechanism was extensively used. When the segments were swept out to the disk or loaded back to memory, and of course, memory was small and expensive those times, so it was quite efficient idea how to run more programs that fit into memory. Operating systems that were designed for sweeping typically had some function that decided what segments sweep out to the disk and which ones load back to memory. It is simply some multi-criteria function with some result value, and we can compare this value for different segments to decide which one should be swept out. Those criteria can concern environment of the program, the size of memory, the size of free memory, and so on. Features of given program requirements. If a program has large segments, it's not easy to load them to memory. So we can sweep out those segments less probably than other ones, because there will be a problem to load them back to memory. Features of segments. When we sweep out the segment of code, we need not write its content on the disk, because the content of segment on the disk is the same as in memory, because we do not modify the code. If it's data, it must be written down to the disk. If it's private, sweeping out stops the program that is the owner of this segment. If it's shared, maybe we must stop a number of programs that use this single segment. Features of the program. If we sweep out one segment of a program, maybe we can sweep out the rest of the segments, because the program cannot run. Execution history. If the program is just loaded, it's no sense to sweep out this program. If a program asks for enlarging memory, it's a good occasion to sweep out this program, because when we load this program back to memory, we will load it in larger memory, enlarged segment, and so on and so on. We can just build a function that takes those criteria into account and just compare the result value of the function of segments in memory and segments on the disk. And if the value for segments on the disk is greater than those in memory, we replace them. And it was quite effective up to the days when the new memory organization was invented. It is paging, but we will discuss paging on the next lecture next week. Thank you for attendance, and see you next week.